Welcome back and good morning. And this is the first class of the fourth module. So, in the fourth module, we have to first see what is the process of sampling, and the most importantly, process of sampling is dependent on a famous theorem, that is sampling theorem. What is sampling theorem? And sampling theorem elaborates the importance of the sampling rate. We'll see that. Then how that is practically done. The process of some sampling is done by some circuits. So how that is done? So sampling circuit we have to learn. And then the reconstruction, we have to reconstruct the original signal from the digital signal, how that is done. So reconstruction of signal, and that is we'll be learning one circuit, namely the zero order hold circuit. So that is one circuit. So these are the first half of the fourth module, and in the later stage of the fourth module we'll see, instead of differential equations, we'll see what is difference equations. So differential equations were for continuous signals. So likewise different signals are for digital signals. So solution of difference equations are also similar. They are also solved, or their response is also found out in a similar way, just as we have seen in the differential equation, that is finding the complementary function and particular solution, or finding the natural response and the forced response and finding that. So having this said this much, I'll just move on with the first topic, that is the process of sampling. So what is sampling? Why sampling is necessary? The reason is that all naturally occurring signals are analog in nature. Whatever sounds we hear from the nature are analog. What the sound of speech, that is analog. Everything is analog. Whatever occurring in nature are analog. But digital thing is not natural. That is artificial. We are making it up. That is. But processing of analog signals is a difficult process. There are so many limitations. So in early 1990s, ASP, that is analog signal processing, were very that was the core area, and that was mainly done by the UC, mainly done by op amps. Op amps, we know the applications of op amp. They can be used as integrators, differentiators, then they can be used as adders, then they then differential amplifiers were there, logarithmic amplifiers were there, a lot of applications were done. So analog signal processing was mainly done by op amp circuits, and but processing speed were very small. Then the circuits were very complex. Lot of difficulties were there. These all things we'll be seeing in the seventh semester when we see digital signal processing. But later it was found that if we convert this analog signals into digital signals were very easy to be processed, and the quality of processing was also very good, and more or less, but when we increase the quality of processing and increase the speed of processing, and it helps in the bulk storage, easiness of storage is also very good in digital, if you make the analog signals into digital signals. So if all these things are considered, but one thing is that if you are achieving more on the other side, we have to pay more. So when you want more when you have the provision to store more signals, or when you have the that is luxury of actually high quality processing, then you have to pay more. That is the only thing which was found disadvantages in digital signal processing. So still digital signal processing are used. You can see that even in in um, uh, in mixers, in musical systems, you have mixers where amplified signal is fed to the mixer, where different tracks are processed and mixed again, so that you get a high quality output outside through the speaker. Okay, so then our mobile phone nowadays, they are also microprocessor based. So every system, every control system are microprocessor based, and microprocessors can accept only zeros and ones. So they cannot, no microprocessor or processor can accept analog signals directly. They understand the language of machine language, that is zero and one, zeros and ones. So how that is done, how these analog signals are made in the form of zeros and one. So the first step in that direction is the process of sampling. That is, analog signals are fed to a sample and hold circuit so that the process of sampling is done. So when you give, that is what is specified in the first line, that is after the sampling theorem heading, that is, a signal, a cosine signal or a sinusoidal signal is fed to a sampling circuit. So sampling circuit is represented by a switch, and over that sampling rate will be marked, rate at which the sampling is done. So switching action is mainly done. Okay, so or continuous chopping at regular intervals is done at at an interval of time t. So when you have the interval of time t, then you can find what is the sampling rate. 1 by t will be the sampling rate. So always the interval of sampling will be specified over that switch, and that is a symbolic representation of a sampler. So when you give any signal, any analog signal through a sampler, you can see that it becomes cos n small omega naught t plus theta. The capital omega is actually in the form of O, whereas small omega will be in the form of W. You can see that. Okay, so what is that actually? That is equal to cos capital omega naught n capital T plus theta. That is the output of a sampler. So you can see that the small t is being replaced by n capital T. That's the difference there. So when an analog signal is passed through a sampler, when an analog signal is passed through a sampler, one thing I'll just 1 minute. Okay, when an analog signal is passed through a sampler, the thing is that the time scale is actually being chopped, or time scale t is actually equal to n into capital T. What is the thing? You can just see the diagram there. That is, a cosine wave is there, and you are actually taking values at regular intervals. That is, you're taking a value at n is equal to 0, that is a maximum value. Then after 0.1 seconds, I'm taking, and I'm assuming, for instance, the sampling interval as 0.1 seconds here. So if that is 0.1, so after 0.1 seconds, again, that is n is equal to 1, you get another value which is less than the maximum value. Then again after 0.1 seconds, you're taking, that is n is equal to 2, you are taking the next value. Likewise it goes. So at n is equal to 0, at n is equal to 1, at n is equal to 3, 4, 5, 6, 7, 8, 9, 10, 11, it goes like that. So at all these instances where at different values of n, so how those positions are marked at different values of n, you are cutting and chopping at regular intervals, and that is, you are chopping the time scale small t into a number of pieces, that is n number of pieces. So what is t now? Now small t is nothing but n into capital T. So when you vary the value of n, you'll get different values of that continuous signal. So one thing you have to understand is that even though you are passing the signal through the sampler, the signal is still a continuous signal, because you are actually finding the values at different points, at different values of small n. Okay, so such a signal, the output of a sampling circuit is not a digital signal, but instead it is called a discrete time signal, because the amplitude is still a continuum. Only thing is that you are chopping the signal at different time instances of time. So the time is discretized, but the amplitude is still a continuum. That is why it is called a discrete time signal. So a continuous or analog signal, after it is passed through a sampler, it becomes a discrete time signal and not a digital signal. That is one point you have to remember. That is, the analog signal which is being passed through a sampler, the output of a sampler will be a discrete time signal, because the time scale is being discretized, not the amplitude. The signal is still a continuum, and And naturally a question will arise, when will this signal become a digital signal? So the output of a sampler or this discrete time signal has to be passed through an analog to digital converter, A to D converter, an ADC. So when this output of the sampler is passed through an ADC, then it becomes a digital signal. So that process, the different ADCs you might have learned in digital circuits course in the fourth semester. Okay, so we'll see all those things in detail when we go to DSP. Okay, so let us take an example where we have a composite signal. So that composite signal has three different frequencies. One is cos 6 pi t, and another is cos 14 pi t. The other is cos 26 pi t. Why this is called a composite signal? Because this signal itself, this single composite signal has three different frequencies. One is f is equal to 3 hertz. The other is 7 hertz. The other is 13 hertz. How did you get that 3 hertz there? Because cos omega t. Okay, so that omega is actually omega is actually given there by 2 pi. So that 2 pi is that omega is given by that 6 pi there, for instance, for the first one. So 6 pi is equal to omega we know it is 2 pi f. So from there you can get the value for f, that is equal to 3 hertz. I repeat, 6 pi is nothing but omega, cos omega t. We'll say that likewise, cos omega t. So there t is there, omega is nothing but 6 pi. So 6 omega is 2 pi f. From there you can find the value for f. Likewise, the first one, the frequency is 3 hertz. For second one, it is 7 hertz. For the third one, it is 13 hertz. Let us take the sampling interval. Just like, I hope you have understood the what is the meaning of sampling interval. That is, that points, if the values of that signal are taken at 0.1 second interval, at regular intervals of 0.1 seconds. So let us take that same sampling interval, that is 0.1 seconds. If that is a sampling interval, what will be the sampling rate? That is a frequency at which we take that point, those values, that is 1 by 0.1, that is 10 hertz. So when a signal is passed through a sampling circuit, it becomes cos. Okay, let us neglect, for instance, for just for avoiding complexity, let us avoid the phase difference, because phase does not have anything to do with this here. So we just avoid, or we just neglect phi and theta. Let's make things very simple. So it becomes cos omega naught n capital T. So when it is passed through the sampling circuit, small t becomes nt. That's all, n capital T. So I have pictorially represented. So what happens when that is done? Then t will be simply replaced by n capital T. Small t will be replaced by n capital T. T is already specified, that is 0.1. So when you substitute, that cos 6 pi t becomes cos 0.6 pi n. Likewise, cos 14 pi t becomes cos 1.4 pi n. Likewise, cos 26 pi t becomes cos 2.6 pi n. Now cos 0.6 pi n cannot be written in any other form. That is that is the same value itself. Then cos 1.4 pi n is equal to cos, it can be written as cos 2 pi n minus 0.6 pi n. That is simply equal to cos 0.6 pi n. And the third signal, that is cos 2.6 pi n, can be written as cos 2 pi n plus 0.6 pi n. That is again equal to cos 0.6 pi n. So these are components. These three frequencies were components of a composite signal. Three different frequencies, that is 3 hertz, 14 hertz, and 7 hertz and 13 hertz. But when these components of a composite signal, when they were passed through a sampler at this rate, that is at t is equal to 0.1 seconds, or fs is equal to 10 hertz, you can see that output of the sampler is the same. Even though there are three different frequencies, everything will remain, everything are equal. Or you can see that high frequencies also possess like low frequencies. So that is called aliasing. You cannot distinguish a signal, a component of a signal from the other component. Everyone remain the same when you take this sampling rate or sampling interval. Okay, so this is called aliasing or aliasing error. The distortion is called the aliasing distortion. So one thing you can understand here, it is that the rate of sampling or the sampling interval has a say. So that should be wisely chosen. Otherwise, things like this will happen. Aliasing distortion will happen. So sampling rate or sampling interval is very important, and that is one of the takeaway from uh, this example. And one thing that is a pointer towards sampling theorem. So what should be sampling theorem? Sampling theorem has something to do with the sampling rate. So sampling theorem will wisely tell what should be the sampling rate then. Okay, we'll move to sampling theorem a little bit later, but let us take another sampling interval or sampling rate. Let us take it as uh, t is equal to 0.02 seconds and fs is equal to 50 hertz. Same procedure. Instead of small t, we replace by n capital T. T you substitute as 0.02 seconds, and what you get is that for cos 6 pi t, it becomes cos 0.12 pi n. For cos 14 pi t, it becomes cos 0.28 pi n. And for cos 26 pi t, it becomes cos 0.52 pi n. So you can see that you cannot write these results after the sampling process in any other form. If at all you can write, that is whatever is inside the argument of cos. Earlier, inside the argument of cos, you had 1.4 pi n. 1.4 is greater than pi n. 1.4 is greater than pi n. That is why you have written it as 2 pi n minus 0.6 pi n. Okay, then again the third component, that is 2.6. Again, that 2.6 pi n is greater than pi n. So one conclusion is there. Here the output of the sampler circuit is distinct because the argument inside the cos function, they are less than pi n. Okay, so another takeaway from this example is that the argument of the cos function should be less than pi n. If it is less than pi n, or even if it is equal to pi n, all the components of the signal after sampling process will remain distinct or different. Okay, here you can see that cos 0.2 or 0.12 pi n is less than pi n. That is 0.28 pi n is less than pi n, and 0.52 pi n is less than pi n. That is another thing. So here you can see that after the sampling process, everything are distinct, every frequencies are distinct and different. So the chosen sampling interval or chosen sampling rate fs is correct. That is the meaning. Okay, let us take a more marginal condition, that is a boundary condition. Let us call, you might have heard in maths about boundary condition. So what is the limit? Okay, what is the boundary between a bad sampling rate and a good sampling rate? That is a margin. Okay, what is that line? We'll find that fine line. Let us take t is equal to the sampling interval as 0.0384 seconds and the sampling interval fs is equal to 26 hertz. So 26 hertz is very important. Sampling rate 26 hertz is very important. Let us concentrate on that 26 hertz, and from that 26 hertz we have got the sampling interval as 0.0384 seconds. So how did you get that 0.0384 seconds? 1 by 26 is nothing but 0.0384 seconds. Let us do the same process. You can see that 6 pi t becomes cos 0.228 pi n. Cos 14 pi t becomes cos 0.532 pi n, and cos 26 pi t becomes cos 0.9984, that is cos pi in itself. Okay, so you have seen that in the composite signal you had 3 different frequencies, that is 3, 7 and 13 hertz. Okay, so I just took that 13 hertz and multiplied that by and find the double of that frequency. So the highest frequency component in that composite signal is 13 hertz. For that component of the highest component frequency here, it is 13 hertz. I doubled it, that is I took it as 26 hertz. Then I found the sampling interval, then I applied that to the sampler, and then I got that for that highest component frequency, the argument of the cos function simply becomes pi n. Okay, so that is the boundary. So that means whenever you choose the sampling rate, that is a boundary. That is, what is the frequency component, the highest frequency component in the frequency in the composite signal. Then if you find the highest frequency component in a composite signal, then the boundary or the margin of sampling rate can be found out by simply doubling that highest frequency. From that you can find the sampling interval and apply. Then that highest component frequency will be the argument of that cost function after sampler will just become pi n. If it becomes above pi n, then the two signals will be the same. Again, the aliasing distortion will come. So that is the point I have to make. So here you can see that again the three signals are distinct. The highest frequency component is just cos pi n, because we have taken the highest frequency component, doubled it, and found the sampling interval and applied. Okay, so that component, the cos argument, will become just pi n. Okay, so it is always wise to keep the argument of that cos function less than pi n, because you never want to work with marginal conditions or boundary conditions, because at any time, due to some external influences, the rate can shift and the entire thing can collapse. Okay, so you don't want to work with that marginal condition, but at least that is the condition. Okay, so pi n, the argument should be at least pi n. Above that, aliasing will come. Okay, so always it is wise to keep the argument less than pi n, just like the second case that we have seen. Okay, so that is what is stated by the sampling theorem. Okay, so before going into the sampling theorem, let us consider one thing. That is, a sampling theorem is defined for an x of t, where x of t is a band limited signal. So we were seeing about a complex signal. What is complex signal? A signal may have, you might see in an explicit way, you might see a frequency. When you see it through a function generator, you see a signal as a single frequency, but that may not be the case, because a lot of harmonics may creep in, or other frequencies may creep in. Sometimes noise may be very significant. So thing is that the waveform will not be a pure frequency. Okay, how that is analyzed, we have learned the Fourier transform. Okay, that is for a or for a Fourier periodic signal, you might be applying Fourier series. Okay, so that you'll find different frequency components. After all, you'll be plotting the for a periodic signal you'll be plotting, or for a periodic signal you will be plotting the spectrum. Let us take a periodic signal, and if you find the Fourier transform, you can actually plot the spectrum. That is, at the bottom you can see, that is along the x-axis you have the frequency, and simply you can plot the phase as well as magnitude, so that it becomes the spectrum. Okay, so thing is that, so when you plot that spectrum, even though it seems like a single frequency, it may not be a single frequency. It has different frequencies, and what is the maximum frequency component in that signal can be found out from that spectrum. So that is the biggest takeaway of a Fourier transform, or that is the biggest takeaway why we convert a signal in time domain to frequency domain. You may be seeing only one frequency, that will be explicit, but implicit, you can see that when you find a Fourier transform or the Laplace transform, you can see that it has many frequencies, and some frequencies will be very prominent in the sense at that frequencies the value of the function or the power of the signal will be very high. Okay, so you can see that here Fm is the maximum frequency component in that composite signal. So earlier we have seen a composite signal where the maximum frequency component was 13 hertz. So here from the frequency spectrum you can see that the maximum frequency component is Fm. Okay, so this Fm determines the sampling rate, like 13 hertz determine the sampling rate. This here in general, the Fm, which is found out from the spectrum after finding the Fourier transform, will determine the sampling rate or sampling interval. Okay, so with this note, I'll just read the statement of sampling theorem. Sampling theorem states that a band limited, so a band limited is that you can see that after Fm there is no x of j omega. X of j omega is 0. or x of j omega means omega is frequency itself, so that is f. So you can write it as x of f is equal to 0 for mod of f. Mod of f means f can be negative or positive. So for negative values of fm as well as for positive values of fm, after that it is all 0. That is what you can, it's clear from the picture itself. So for f greater than or equal to fm, or mod of omega greater than or equal to omega m, that is whether omega is positive or negative, after omega m it is 0. X of j omega is equal to 0, can be represented into, and uniquely means after the sampling process you should get a distinct 3 different or that much different signals. So uniquely determined from its samples x of t omega t and nt, if the sampling frequency fs greater than or equal to 2f, 2 times. So always this is the condition. You should not take fs equal to 2f, or you should not take just like the previous example, fs is equal to 13, fs equal to 2 times 13. If that is done, the highest frequency component after the sampling process just becomes, the argument just becomes pi n. That is a marginal value, that is a boundary condition. Okay, you should never do with that, but at least that should be greater than or equal to, at least that should be equal to 2 pi 2 fm, and always for satisfactory operation that should be fs greater than or equal to 2 times fm, where fm is the highest frequency component present in it. So in middle stages it can be represented into and uniquely determined from its samples x of nt. See, if this condition is not satisfied, so see, after all, this sampling process is done to convert the signal, that is discrete time signal to, or analog signal to discrete time signal, and discrete time signal is after converted that into a digital signal by passing it through an ADC. So this digital signal after processing has to be reconstructed into an analog signal, because if you pass a digital signal, that is zeros and ones, through a loudspeaker, you cannot hear anything. Or if you have a mobile phone, and if you have when you hear something, you cannot hear zeros and ones through the receiver. It's not possible. So after processing, the reverse processing should happen. That is, whatever processing that we have done, that should be brought back. That is, digital to analog converter has to be used, and the digital signal has to be converted back to analog signal. That is, we require analog signal. Processing is only done in the digital domain. Whatever we have given, that should be that we have to get back. So analog signal has to be reconstructed from the digital signal. So reconstruction of digital signal is only possible if the sampling rate is correct. That is, fs is greater than or equal to 2 fm. Okay, so having said this much, I hope you have understood what is the process of sampling, why the need of sampling, and how that sampling is done, and who determines the sampling rate. Okay, and these are the things I want to elaborate in the first lecture of the 4th module, and in the next lecture we'll see what is a sampling circuit and the reconstruction circuit. Okay, till then, goodbye. Thank you.